Hello and welcome to another one video. Why hasn't graphene taken over the world yet? Let's define what graphene is first. Graphene? Graphene is a sheet of a single layer, monolayer, of carbon atoms tightly bound in a hexagonal honeycomb lattice. Graphene is often called the wonder material. This is because graphene is arguably the strongest material as well as it is completely flexible. It is more conductive than copper itself. It has incredible potential to make everything better and more durable. Now with that in mind, why hasn't graphene being embraced by industries and other companies? Well, it revolves around two main things. Money and research. According to Libram analyst Yuan Lo, at the moment, 1 gram of graphene is estimated to cost around $100. With things like this, commercialization takes years. It'll spend years in the lab and then years in trials and scale up and so on. I mean seriously? 1 gram of graphene for 100? Not really the best choice. On the other hand, graphene sounds nice, but take into consideration that graphene can be dangerous. As stated, graphene is more prone to conduct heat and electricity. It is 1,000 more times conductive than silicon. Currently it is very difficult to produce graphene in large amounts that has no defects or faults in its atomic structure. Research is still needed to understand graphene better. Also error rates. According to Chegg.com, it's estimated that a 1 centimeter chain of bonded carbon atoms would have about 70 million carbon atoms. If you made a 1 centimeter square sheet, that might have 4.9 trillion carbon atoms. Now suppose you have a manufacturing process that is 99.999% error-free. That means in a 1 square centimeter sheet of graphene, you would have 4.9 billion errors, bad bonds. In practical effect, that means it falls apart and you get tiny flakes. Physics is so far not our friend on producing useful sizes of graphene, let alone doing it in an affordable fashion. Is graphene overhyped? Graphene isn't as much overhyped as it is usually the media misinterpreting what graphene can be used for. The biggest market is in electronics, but while many news sources claim new electronics from graphene, they fail to realize that graphene's problem is that it has no band gap, so it is not a semiconductor. Therefore, graphene at best can only be used for metallic applications, i.e. wiring, interconnects, electrodes, etc. In fact, there are companies in Korea developing OLEDs where graphene is the transparent electrode, definitely showing that there is potential for the material to transcend lab benches. The second problem is that all the commercial applications of graphene rely on chemically grown, CVD, graphene. But most papers and news reports are on exfoliated graphene, which has superior electrical properties. This is actually a result of graphene grown on copper and then transferred to an insulating substrate, i.e. silicon dioxide, sapphire, or some other oxides. The actual growth process can already make single crystal graphene up to a wafer size. However, after transferring it to a substrate, there is polymeric amorphous carbon residues and/or defects which arise due to the etching of the original, copper, substrate. Ultimately, this reduces graphene's electrical properties. So in simple terms, graphene actually does has some promise in electronics that do not require extremely good electrical performance, i.e. TFT-based electronics or maybe something like batteries where graphite graphene oxide are commonly explored electrodes. As for mechanical applications, I do agree that it may be a bit harder. Graphene actually is not predicted to be stable when it is fully suspended. Naively, this can be imagined as strong molecular forces will cause graphene to naturally wrinkle and fold onto itself to form a more stable 3D bulk. However, for what it's worth, there are many sport companies which add graphene, or graphene derivatives, into their products to advertise superior mechanical performance, think rackets or skis. Additionally, many propose military applications like Kevlar for graphene, though even if it is developed, it may be a bit harder to hear about. Most of these rely on just adding a dispersion of graphene or graphene nanoparticles into some composite material. So I don't think it's entirely fair to say it's gone nowhere. IGZO is just becoming common as the semiconductor material for displays, but was developed as early as 2003. IGZO is also a material which can be easily grown via scalable methods and more readily compatible with traditional technologies. With that in mind, the investment needed for a graphene infrastructure and that the cost-benefit of switching to graphene for many materials is not worth the savings profit. Also, keep in mind that while graphene was discovered in 2004, that was just from exfoliated graphene, and chemically grown graphene was not available until the late 2000s near 2010. As growth techniques do become more and more readily scalable and more problems of graphene are solved, It definitely has potential to be incorporated into more products. Because Korea also holds many patents on graphene, it is inevitable